Hi everyone. Most of you, I guess, know me already. My name is Mareike Fischer. I am working at the University of Greifswald in Germany. And as you can tell, it's winter here. I would rather be in Tasmania right now, believe me. But given that that's not possible, I still enjoy the fact that we are all making the most of it. I enjoy this conference very much. Thanks a lot to the organizers of Philomania, and I hope you will also enjoy my talk. Here we go. So my talk today is about what I call a new attempt at future-proofing consensus methods. And I will, of course, also tell you what the old attempt was, because not all of you might have heard of this. And the property that consensus methods may have and that I'm going to introduce now is called refinement stability. And this project is actually joint work with Michael Hendrickson from the University of Düsseldorf, whom most of you already know, and who is also a participant of this conference. Okay, so let me just quickly remind you of what the main idea of consensus methods is. So given a consensus method phi, what it does is the following. It takes a collection of trees, also called a profile, P, T1 to Tk, which are all trees on the same taxon set, but they need not be binary or anything. So what this is really, a profile is just an ordered tuple. So you might also have the same tree appearing here multiple times. So such a collection of trees is taken by our consensus method and turned into a unique tree, which we then call the consensus tree phi of P. Okay? So this is just a made-up example. Now you might have these two trees, T1 and T2, in your profile, and then you want to combine them to give you one common tree, and depending on your consensus method, the tree that you get might look like this, or it might not. So it might look completely different depending on your consensus method. In this case, you already see that the consensus tree need not necessarily be present in your input set. Okay? And this example now was for rooted trees, but of course the same procedure would also work for unrooted trees. And all of the results that I'm going to talk about in this talk, actually that I present for rooted trees, also hold for unrooted trees. Okay, so I will not explicitly state that all the time. At the end of my talk, when we come to MRP, there are some results which only hold for unrooted trees, but whenever you see a rooted tree, the result also holds for unrooted. Okay, so why do we need consensus methods? Well, there are many instances in phylogenetics where you're presented with many trees. For instance, if you do a Bayesian tree estimation based on your data set, on your DNA, RNA, or protein data, and you run your Markov chain Monte Carlo method, and then you have a tree sample, and you want to get the consensus, yeah, so to speak. Maybe you could think of this as the average tree. Or you might have analyzed multiple genes of the same species set, which can lead to different trees, because not all genes necessarily have the same gene tree. And the other thing that sometimes happens is that you have one data set, say one DNA alignment, and you use different tree reconstruction methods to get your tree back, and turns out that different methods sometimes return different trees. And then you might think about, well, what's the consensus of the output trees that I got, and so forth. So there are actually many instances in phylogenetics where you have multiple trees and you want to combine them into one unique tree, and this is where consensus methods come into play. So what exactly is a consensus method? A consensus method, phi, is just, mathematically speaking, a function that assigns a unique phylogenetic X tree, phi of P, to a profile P on phylogenetic X trees, T1 to Tk. So the important thing here is, and this is what we will later see distinguishes consensus methods from supertree methods, is that both the input trees as well as the output tree here are all on the same taxon set X. Okay, this is different when you talk about supertree methods. Okay, So some examples that most of you probably know. There's a method called the strict consensus. The strict consensus is a very simple thing that's also very restrictive. It takes a profile P of phylogenetic X trees and returns the unique tree which contains only clusters that are contained in all of the input trees. Okay, I'll show you an example in a minute. The other thing you could do is you could use the so-called loose consensus. The loose consensus takes such a profile and returns the unique tree which contains only clusters contained in at least one of the input trees, but such that they are compatible with all of the trees. So if you have a cluster, it is sufficient for the loose consensus if it appears once in your input set, as long as it's not contradicted by any of the other trees. So here's another consensus method that probably most of you know, namely the so-called majority rule consensus method, which always needs to be specified according to some percentage P that you have to predefine. So what it does, it takes a profile of phylogenetic X trees and it returns the unique tree which contains only clusters that are contained in more than P% of the input trees. Except in the case where P equals 100, you can't have more than 100%, so in this case 100% would be enough. But typically you assume P to be 50 and then you would be returning a tree containing all the clusters that are contained in more than 50% of the trees. Note that if you take P equal to 100, what you get is the strict consensus. So the strict consensus is just a special case of the majority rule consensus. Okay, let's look at some examples. So assume you have this input profile of trees. Let's look at what the different consensus methods would do here. And let me see if I can manage to, yes, I can write here, just a second, maybe also choose a nice color. Let's go for red. Okay, so the strict consensus would look at all the clusters that are present in all of the input trees. And as you can easily see, for instance, the cluster 1, 2 is present here, the cluster 1, 2 is also present here, and the cluster 1, 2 is also present here. So the strict consensus would return the tree that contains the cluster 1, 2. But in this case, no other clusters because, and you can easily verify this, there's no other cluster contained in all of the trees. Now, what would the loose consensus do? The loose consensus would look at all the clusters that are contained in any of the input trees and look if they are contradicted by any of the other input trees. So for instance, of course, the cluster 1, 2 has to be in the loose consensus as well. That's contained in all of the input trees even, so not contradicted anywhere. But for instance, the cluster 6, 7, let me choose a different color now. The cluster 6, 7 is contained here. It's even also contained here. So it's not contradicted here. And it's also not contradicted here because 6 and 7 are in the same cluster with 5 here, which is fine because 6, 7 would be a possible subcluster of this cluster. So there's no contradiction. So this is why the loose consensus contains the cluster 1, 2 as well as the cluster 6, 7 and actually also 3, 4 for the same reason. Maybe I take a different color for that. Let me see. You have 3, 4 here, you have 3, 4 here, and you have this a supercluster that also contains 3, 4 here. So you could have 3, 4 versus 5 that would be compatible with this scenario. So this is why the cluster 3, 4 is here. However, there is no agreement where taxon 5 should go. So here, according to this tree and this tree, taxon number 5 should be in a cluster with 3 and 4. But here it should be more closely related to 6 and 7. So there's some conflict, which is why the loose consensus does not put taxon 5 into any cluster. Okay, what about the majority rule consensus? the majority rule consensus looks, if we look at here, I said P equals 50, so which clusters are contained in at least 50%. Of course, again, our cluster 1, 2, that's contained in all of the trees, and 6, 7 is contained in 2 out of 3 trees. 3, 4 was also contained in 2 out of 3 trees, so that also has to be here. And as I have already mentioned, 3, 4, 5, this pink one here, and if you extend this here, it also gives you 3, 4, 5. So actually, the cluster, this is this branch here that cuts 3, 4, and 5. This also needs to be in the majority rule tree. Okay, but you can easily verify that there are no other clusters. For instance, here 1, 2, 3, 4, 5. That would be this branch here. This is not supported by the other trees. So we have here 1, 2, and 6, 7, and this is 1, 2, and 5, 6, 7. So there are no other clusters, and in particular, the 1, 2, 3, 4, 5 is not a cluster of the majority rule. Okay, so in this example here, you can easily see that it's possible for all these 3 consensus methods to give you different output trees. So yeah, we have to think well which consensus method to use. So we want to find sensible consensus methods. And one way of saying what is actually sensible is to search for so-called regular consensus methods. What makes a consensus method sensible? Well, there are 3 properties that you would at least expect of a good consensus method. The first is called unanimity. Unanimity means that if your input profile contains only a bunch of copies of the same tree, then the consensus should, of course, be exactly this tree. Okay, so if the input trees all agree there is no conflict, then a sensible consensus method should for sure not return a different tree. Then you want anonymity. Anonymity means that if you change the order of the trees in P, this does not change the consensus. So this is because we defined P to be an ordered tuple rather than a multiset. So we have an ordering, but we basically want that we want this not to matter, right? This should not affect the outcome of our consensus method. And neutrality, that's the last one that we require as a minimum standard for consensus methods. Neutrality means that if you change the leaf labels of the input profile, this should just swap the leaves of the output tree in the same way, okay? So, for instance, if you swap the roles of cat and dog in your tree, this should really only swap the roles of cat and dog in the output tree. It should not give you a completely different structure of a tree just because you swapped 2 leaf labels. If all these 3 criteria are fulfilled, and this is basically a concept introduced by Brian, Francis, and Steele in 2017. They looked at these 3 criteria, and if they are all together fulfilled, they called such consensus methods regular. Okay, so, and these, as I said, these are like things that are really biologically plausible and make a lot of sense. So this is like the minimum requirement that you would expect a consensus method to fulfill if it's sensible in any regard. So, are there examples for regular consensus methods? Yes, there are. Actually, the strict consensus is regular, loose consensus is regular, and also majority rule consensus is regular. So all 3 consensus methods that I've just briefly reminded you of are regular. Okay, but I said my talk would not be about like sensible consensus methods or regular consensus methods, but about future-proofing consensus methods. And I said we are trying like something new now, but there has been a first attempt at investigating whether or not there are future-proof consensus methods. And what would future-proof actually mean? Well, the question is which consensus methods are robust concerning the introduction of new or additional information. So if you gain more insight, this should refine your knowledge about the consensus, but not contradict your previous findings. Okay, because if your method is such that it only ever can reflect the state of the art, this might not like make so much sense. If you, for instance, discover a new species tomorrow, and if you know already this might change the entire structure of your consensus tree, then this makes your consensus tree maybe not so trustworthy. So in the sense of Bryant, Francis, and Steele, this was exactly what they were looking at. They were looking at regular consensus methods and looked whether or not these were extension stable, so robust concerning the introduction of new taxa. And so what does extension stable mean? Mathematically speaking, it really just means that if you have a taxon set X and a subset Y, which is non-empty of your taxon set, then a consensus method phi is called extension stable if phi of any input profile P and any such subset Y of taxa, if you restrict the input profile on this subset, then this gives you a consensus tree, phi of P restricted to this subset. And if you take phi of P and like the original profile on taxon set X and run the consensus method on this, like on the big taxon set, and later on restrict it to the smaller subset, then this should basically refine. So this is the phylogenetic in phylogenetics, the symbol, the mathematical symbol means it refines. So this tree refines this tree. So that means if you have more taxa that you analyze, this might basically lead to some new clusters in your tree, but not to any clusters that contradict the original findings on the smaller set of taxa. Okay, so this is what they said called extension stable. Okay, but they found that unfortunately no regular consensus method is extension stable on all possible profiles. There were some positive results concerning restricted version of extension stability, but I don't have time to go into the details here. But basically, no regular consensus method is extension stable. So in this regard, no regular consensus method is future-proof. Woof, bad news. But remember our main idea. We said future-proof means if you gain more insight, this should refine your knowledge about the consensus but not contradict your previous finding. But more insight need not necessarily mean that you discover a new species, right? In fact, what happens maybe even more frequently is that that you are able, your new insight is that you are now able to resolve a formerly unresolved cluster. And we call this, if a regular method is robust against this kind of new knowledge, we call it refinement stable. So let me just also formalize this. So if phi is a consensus method, and if this method for any pair of profiles P and P prime, so they have the same number of trees, K trees, and P prime contains trees Ti which all refine the corresponding tree in the profile P. So if for any pair of profiles P and P prime that have this property that P prime refines P, then the consensus of P prime also refines the consensus of P. If this holds, then phi is referred to as a refinement stable consensus method. Okay. Which methods are actually refinement stable? Well, the first result that Michael and I came up with is that majority rule and strict consensus are refinement stable. And as we have already seen, they are also regular. So as opposed to the really bad news by Bryant, Francis, and Steele, who found that regularity and extension stability cannot be fulfilled at the same time, in fact, refinement stability and regularity can be fulfilled at the same time, and they are fulfilled by majority rule and strict consensus. the idea of the proof, for which I probably don't have much time now, but the idea is you look at majority rule. Strict consensus is anyway just a special case of that. And because you require that, that your P is such that more than 50% of all input trees contain all the clusters. And if you now discover a new cluster, unless it's contained in more than P% and P is at least 50, so it must be contained in more than 50% to affect the outcome, to affect the consensus tree. So that means, because it's more than 50% in any case, no matter what your P is, that means that for any pair of clusters, so your new cluster and the cluster that has been there before, there's at least one tree where they occur together. So that means that you are guaranteed that the new cluster, whatever it is, if it occurs so frequently in your input set that it affects the consensus tree, then it must be pairwise compatible with all of your other clusters that appear so frequently. So it must be compatible with all clusters in your consensus tree, which means that majority rule will simply incorporate the new cluster into the consensus tree and no harm is done. So this is basically the idea of the proof. Okay, but loose consensus is not refinement stable. And here's why. So you can simply look at this example here. You have this so-called star tree on 5 taxa, and we have the tree here, which only has the cluster 1, 2, and otherwise everything is unresolved. This is my profile P, and the loose consensus tree of this tree, these trees, is of course this second tree here, right? Because this tree has no clusters I need to consider, but here we have this cluster 1, 2, which is present in at least one input tree, namely here, and it's not contradicted by any other input tree. So the loose consensus would be this tree. However, if I look at P prime, which consists of these two trees, then the loose consensus would be the star tree, because here we have to look at the cluster 1, 2, but that contradicts the cluster 2, 3, because here 1 is more closely related to 2, and here the 2 is more closely related to 1, and here the 2 is more closely related to 3. So this is a contradiction. So the only cluster, this one, and the only clusters, namely 1, 2 and 2, 3, which we have to consider, are not compatible with the other input tree, respectively. So what happens is the consensus is a star tree. But note that this this tree here is, of course, trivially a refinement of the star tree here. So this profile P prime refines P. This tree has remained unchanged, and the star tree has been replaced by a refined version, but still the outcome is a coarser version of the original tree. It's not refined. We lost a cluster. We lost the cluster 1, 2, going from P to P prime. So loose consensus is not refinement stable. So majority rule and strict consensus are refinement stable, but loose consensus is not. What about other methods? For instance, let us consider MRP and MRC, matrix representation with parsimony and matrix representation with compatibility. I only want to really briefly look at those. Why only briefly? Because they are actually not consensus methods. They have been introduced as supertree methods. And there is an ongoing debate whether or not they can legitimately be considered consensus methods. If you are interested in why that is, please look at the work by Olaf Bininda-Emmons. He's written some interesting papers, and also his book states some aspects on how to use these as consensus methods and why they are good as such or not. They can be used as consensus methods, as you can see in David Bryan's 2003 classification paper on consensus methods. So this is why I briefly want to look at them here. So what are supertree methods actually? Well, the main idea that they have is also take a collection of trees, a profile, but here as opposed to consensus methods, there is typically some overlap in the taxon sets, but the taxon sets for sure do not have to be identical. And so the trees might look like this, right? Here taxon 5 is missing, here taxon 3 is missing, for example. And then what you get is an output consisting of a set of trees, so-called supertrees. Sometimes, of course, this set only contains one tree, that's possible, but typically it's a set of trees incorporating all taxa of the input trees. So for instance, here, totally made up example, for these 2 input trees, you might end up with these 2 output trees on 5 taxa. Okay, so what's the problem? How can we use this as a consensus method? Well, we need to make sure that our input consists only of trees on the same taxon set. That's something we can easily fix. That's not a problem. But yeah, if we then calculate the set of supertrees, it might still be a set of cardinality at least 2. So there might still be more than one supertree. And then in order to return a unique tree, which we need in order to have a consensus method, we could decide to return the consensus of the supertrees according to some consensus rule, for instance, strict consensus. So typically supertree methods require a consensus method in order to be used as a consensus method, which is maybe the main reason for the ongoing debate whether or not this is sensible. Now, MRP and MRC are 2 supertree methods that fall into this category. And I don't have time to explain all the details, but what they do is they take the input trees and code them as alignments, or you could call these matrices. For instance, the first tree here, oh, where's my pointer? Here. The first tree has the internal branch that separates 1, 2 from the rest. So here the first column separates 1 and 2 from the rest. The second internal branch separates 4 and 5 from the rest. That's this second character here. For the second input tree, you could do the same. Then you have 2 alignments because you have 2 input trees, and then you can combine these alignments to form one big alignment. Now, this is not a real data alignment. This is really just a way to code your trees, to uniquely code your trees in form of such binary alignments. And now for this alignment, basically you can treat it like a data alignment and run some tree reconstruction methods on it. For instance, parsimony or compatibility. So I've here highlighted the maximum number of compatible columns. This is in this case 3. All 4 are not compatible because the second and the fourth character here happen to be incompatible. So if you take the first 3, that gives you this tree, but there's another set of size 3 of compatible characters here that would give you another tree. So MRC would give you these 2 trees. And in this example, this is a really trivial and basic example, MRP, so if you run maximum parsimony on this alignment, it would return the same 2 sets, the same set of 2 trees here. Okay, and as you can see in this trivial example, we haven't really gained much because these were actually our input trees. But generally, this need not be the case. The input trees need not be contained in the set of output trees. Okay, so you have a set of trees and you want to turn this into a unique consensus tree, so you have to finish this with the last step, namely to give a consensus, and I decided here to go with a strict consensus, which was also suggested by David Bryant in his 2003 paper. So in this case, this would then be your consensus tree. Okay. So are these refinement stable methods? No, MRP and MRC are not, and this does not depend on the consensus method you use to summarize the supertrees. Okay? They are not refinement stable because the counterexamples that we generated basically produce a unique output tree anyway. So it doesn't depend on how you summarize the output of the supertree methods. And there are other well-known methods that I can't discuss today, Adams consensus, Ahaus consensus, that also turned out to not be refinement stable either. So the question then arises, is being refinement stable special? Because we have seen so far only majority rule, including strict consensus, are refinement stable and regular. Are these the only two methods with this property? And it turns out no. Surprisingly, there are actually infinitely many regular and refinement stable consensus methods. Okay, so here are some things for discussion and also some hints at our ongoing research. So we are looking at other established consensus methods because, I mean, there are at least 13 different methods listed in David Bryan's classification paper. And we have so far only looked at 7 of them. Also, question is that this set of infinitely many regular and refinement stable consensus methods that we came up with, does it actually contain any biologically sensible ones other than majority rule and strict consensus? Are there any more methods that we could discover that would be interesting for biologists, right? If we could come up with new consensus methods that maybe also have these nice properties. And another question is, since regularity and refinement stability are now not unique to majority rule and strict consensus, are there maybe any other properties that make them unique other than, you know, the trivial ones given by their definitions? So, conclusion, there is still much work to be done. And yeah, with this, I basically want to thank my co-author, Michael, the organizers of Phylomania. Thanks again for this great conference. And thanks to you for your attention. Thank you very much. And I want to finish this with at least one cartoon because most of you basically wonder, and this is also anticipating the first question that you might have, Mareike, where are your cartoons? Well, this is an online talk and I was slightly afraid of the copyright, but here's one cartoon by my daughter and I'm pretty sure she will not sue me. So, are there any other questions?